Welcome to the video lecture series for HEAL 518. This lecture covers basic epidemiological statistics and how some of those statistics are calculated. So what I'm going to cover are some measurement basics. I'm going to clarify the differences between proportions, rates, and ratios. These are three common measures that are used in epidemiology and are often confused when reported by epidemiologists, but also when you see in the media these terms used, they're often used incorrectly, so I want to just clarify them. I'm also going to share two categories of how we measure things in epidemiology, and there are kind of two areas I'm going to cover. Actually, three different topics I cover here. I'm going to skip potential impact of intervention as an area of measurement because I'm going to cover that in a different way in class. But these two areas are really important. So first I'll talk about measuring disease frequency. And you probably have heard prevalence and incidence a lot. I'm going to go in depth about what they actually mean and how they're measured and calculated. And then I'm going to talk about measuring effective exposures and specifically looking at odds, ratios, and relative risk. So if you're doing a case study, you're going to be looking at odds ratios. And if you're doing a cohort study, you're going to be looking at relative risk. So here we go. Just a reminder about epidemiology. If you've never taken epidemiology, but we are in the middle of a pandemic, you're being thrown into epidemiology every day of your lives. A reminder about the epidemiological triangle. This is the underpinning of how we think about disease and its interaction, the interaction between elements of disease in the world. So there are three elements to this triangle. Obviously, it's a triangle. First, let's start with the agent. There's an infectious disease of some sort of microorganism, and it's classified based on many things: its size, its structure, its physiology. So, for example, influenza has specific physiology. It is obviously a microorganism that's been characterized as different types like A and B, and so on. Hosts are organisms, usually human, but can be animal, that harbor the disease, that can pick it up. We can pick up influenza and become reservoirs for that disease. And then in the environment plays a huge role in this. So these are the surroundings or conditions that are external to that human or animal host that cause or allow the disease to transmit. So for example, being outside and socially distanced away from people actually improves or reduces the likelihood of transmitting COVID-19, for example. And so these things are an interplay. There's a relationship between these three things that make us understand how disease burdens the world, burdens human beings, animals, and perpetuates in society. So it's really important to understand these concepts and these terms. This is not a course on epidemiology. I encourage you to take one if you've not taken one. But just know this is kind of the underpinnings of thinking about epidemiology. And as we get into measurement basics, be thinking about those three things and how they interact. So let's get into the basics of measurement. So epidemiologists most often compare things. We'd like to compare usually two things, and we use ratios, proportions, and rates to make these comparisons. And we sometimes make mistakes actually in using these different types of measurements. So I want to clarify and define each of these. So first of all, a ratio. This is a quantitative comparison telling how much of one thing there is compared to another. We'll often see a ratio as having a semicolon in the middle, or a colon in the middle between two numbers. Sorry, not a semicolon. A comparison of two things, there's one thing on one side and one thing on the other. So visually, you can kind of see a ratio in your mind. A proportion is a part of a whole. So we're looking at one thing in our hand out of the entire thing, a piece of the pie. Rate is the frequency of an event in a defined population during a defined period of time. And so often when we're thinking about things that happen in epidemiology, we're usually talking about rates. But the other two are usually confused. particularly in the news media. I see these things confused all the time. And so as you're looking at news media tonight, see if any of this is confused in your reading, and you'll be like, aha, there's no defined period of time here. This is a part of a whole, not a rate. And you'll feel really good about yourself and being more of an epidemiologist than you ever thought possible. So these are the three definitions. So let's take a closer look at these and how they make sense with an example and do some math. So in a particular year, the CDC received 2,365 Lyme disease case reports. So imagine there were about 1,572 cases in females, 793 cases were male. And so for the purposes of this, I'm just going to focus on sex assigned at birth as reported to CDC. Okay, so we're going to look at ratio. So quantitative comparison telling us how much of one thing there is compared to another. Okay, so I've set up in my table females on one side, males on the other with my numbers of cases. So to set up the ratio, I've got my colon in the middle, my 1572 colon 793. I'm going to do my math by dividing females by the number of cases of males and multiplying by 1. And the number I get is 1.98. Now, it doesn't look like you've got a colon in the middle anymore, and this is why people get really messed up about ratios, because they expect to see two numbers and a fancy colon in the middle. No, it's a number. So how to say this in epi language to know that it's a ratio? So you can say that there were 1.98 Lyme disease cases in females for every one case of Lyme disease in males. So we're standardizing the number of cases from one type of case to the other. So it compares, again, quantitative comparison telling you how much of one thing there is compared to one unit of the other. And it's typical to standardize it based on one unit of one thing. So in this case, because there are more cases in females, you typically take the larger of the two and you divide that. So you choose one that is the largest, you then divide that by the one that isn't, multiply by the number that you want to say for every X unit. So in this case, it's 1 by 1. So you don't actually have to multiply by 1. But if you wanted to say for every 2, you could, and then you would do slightly different math. But in this case, that is the expression that you would hear to know that that is a ratio. For the rate, and I'm going to skip to the rate instead of the proportion just quickly here. But again, frequency of an event, defined population in a defined period of time. My same table, I'm going to set the math up here, but my total number of cases, I need my total number of cases to do the math. So I've added the both female and males together, and total number of cases is 2,365. Remember, I'm trying to understand the defined population, so I need to find what my total population is. All right, great. So on one side, females, I take the entire group. I do what I see as a proportion here. So this is a report. You'll see a proportion here, 1572 out of 2,365. That gives me 0.66 for females. I do the same math on the other side for males. And then because rates are usually expressed per standardized unit of the population, so you'll see per 1,000 people, per 100,000 people is a typical expression for rates. You'll see that the frequency will be expressed in that way. So we're going to multiply, in this case, per person unit of 1,000. So 660 is the number we get for females, and it's 340 for males. So how do I say that in epi language? The frequency of Lyme disease is 340 cases per 1,000 males and 660 cases per 1,000 females. So that's the rate. So I mentioned proportion a moment ago, and I already calculated the proportion, but you can kind of see how you're set up to do a rate with the proportion. It's part of a whole. I already calculated that total. I have the number of cases in one category divided by all the cases. So how do I, again, state this? I've got the total number of cases. I do the math by dividing the number of cases in one category by the total number of cases, multiplying by 100, so I get a percent. And then I can say that 34% of the reported Lyme disease cases were males and 66% were in females. And so again, this is proportions of a whole, so total of a whole, or part of a whole rather. So the very different language you use to describe these. Again, ratios are always going to be a quantitative comparison of two things standardized based on a unit. Rates will usually be expressed as per a population unit based on a discrete unit of time. And a proportion, it needs to be used to calculate a rate, but it often is confused for a rate. So a lot of people say, well, 66% of people, the rate is 66% of some group. And you'll be like, that doesn't sound like a rate. That sounds like a proportion. And that is a snapshot in time of the proportion of people in a specific category at any one given time. Sure, but it's not expressed as a rate. It isn't standardized to a group of specific number of people, like a state, or per a specific period, like the year 2020. And so that needs to be handled well. So getting a handle on this language and this math is really important. All right, so let's move to the first category of measurement, and that is disease frequency. And everyone needs to get this right in epidemiology. The two main ways you can do that are with prevalence and incidence. Now, prevalence. This is the number of existing cases of a disease in a population at a specified time. And again, a lot of people just report prevalence and thinking they don't need to actually say what date it is. Yes, you do. You absolutely do. It's usually expressed as a proportion or a rate. You can use both. This is an example of a proportion. So obesity prevalence trends in both children and adults based on two-year rolling years. And this is from the NHANES. I believe this is the NHANES survey, is it? Yes. And this is from 2007 all the way up to 2016. And so it's looking at different obesity categories. So this tells me the proportion of kids and adults fitting in these categories at different time points. Great, this proportion example. So prevalence can be expressed at one point in time or over a certain period of time. So point prevalence is the prevalence of a disease in a population at a single point in time. For example, today or in the year 2020, you might actually think of this as slightly different, but today the prevalence of diabetes is 10%. And that might be considered as a proportion, expression of prevalence as a proportion. But period prevalence is the prevalence of a disease in a population over a specified period of time that includes cases at the start of the period and any subsequent new cases. So this could, for example, we see on a lot of the COVID-19 trackers, the average 7-day not the average 7-day cases, that's incidence, but if you look at the overall in 2020, when the year is over, you can actually calculate the prevalence of COVID in the population over the entire year, as opposed to saying on a given day what the prevalence is. Calculating prevalence is relatively straightforward. So the prevalence of hysterectomy, for example, in a population of women or people who have uteruses, who are aged 50 to 75 can be calculated. In this example, recruited 1,200 women, and they found out that 97 of those women, people who identified as women, had hysterectomies. So we can do some math here. Prevalence is the number of existing cases out of the number of people in a study population. So the prevalence can be, in this case, 97 out of 1,200, which is 0.08. To get the percent, you have to multiply by 100. And you can go as many decimal points as you want. It's customary to go at least one, but the minimum of just the whole number is fine. The prevalence of hysterectomies among this population is 8%. At this point, this is a point prevalence. So if we're going to calculate the prevalence of obesity per 10,000 people in Virginia, again, this is a rate, we now need to know the total number of people in the state in order to be able to do that. Again, because we need to know the total population to be able to make that calculation. The population of Virginia as of 2016 was around 8.4 million, and we know the number that were obese or identified as obese was around 2.4 million. So we can take that 2.4 million, divide by 8.4 million roughly, and get 0.2899. And then if we multiply that by 10,000, because that is the unit that we wish to express the rate in, then the calculation that we have again, is expressed as 2,899 per 10,000 people in Virginia are considered obese. So again, you're not standardizing this as a percent or multiplying it as a percent. In order to be able to standardize this, you have to be able to express it in the unit that's appropriate here. And because you have 4 zeros there, you have to then move the decimal point over by 4 in order to account for that. Great. Okay, so what is incidence then? So within a particular population, incidence is the number of new cases of a disease during a specified time divided by the number of persons that are actually at risk of a disease at a specified time. And that part, at risk, is the one part that throws a lot of people off. So again, new cases only. So these are individuals who have a disease, these are individuals who develop a disease. If you are an individual who has currently has that disease, you are not part of the calculation. So if you're calculating breast cancer incidence and you already have breast cancer, you are no longer part of the calculation. Measures of risk. This marks change in health from disease-free to diseased. So you're moving from one thing to the other. So what is that measure of risk? That's what we're trying to understand with incidence. And what does it mean to be at risk? So free of disease of interest, but capable of developing it. So for example, prostate cancer, only men or people who have prostates can be in the calculation, because women or people who do not have prostates cannot do not have prostates. They're not at risk of developing prostate cancer, so they are removed from the denominator of the calculation. This is important. Again, you cannot include people who are not at risk of the disease at the specified time in the calculation. So here's an example of what incident looks like when it's graphed, and this is a recent example of COVID-19. So in contrast to prevalence, looking at prevalence of disease in a population at any one time, we've been tracking COVID, for example, across the pandemic, but this is from the very first year, starting at the very beginning of tracking in March of 2020 by age group. And this is a trend line, so you can look at the incidence of new cases per 100,000 calculated using the US Census population, because it's common to standardize the data based on the census population using as sort of a denominator. So how many people live in the US, and to use that as a standard for how many people are at risk for the disease. So what is incidence overall in terms of type when we think about cumulative incidence? Well, that's the proportion of people who developed outcome of interest during a specified block of time. So, for example, cumulative incidence is the number of new cases accumulated over, for example, 7-week time. So if you're looking at a COVID tracker and you see the average number of cases over a 7-week or 2-week period, that's cumulative incidence. Incidence rate is a true rate, so whose denominator is the total of the group's individual times at-risk person time. So it's important to understand that we have to have the exact right denominator. We have to really think about who should belong in that denominator. That calculation needs to be correct. How to calculate incidence. So let's work that through with an example. And again, it's the number of new cases over the total people at risk in the population, and that could be for public health, it could be the general population, it could be a study population. So let's look at a study population. So what is the incidence of uterine cancer in a population of women like we had done previously? So imagine we recruit 1,200 women who had 97 hysterectomies. So let's do math again. So without a uterus, no longer at risk of developing uterine cancer. So we've got 1,200 minus 97, that's 1,103 women at risk of developing uterine cancer. We have 27 new cases of uterine cancer that are observed over the years. So that means that our incidence is 27 over 1,103. And then that equals 0.02. To get the percent, we multiply by 100. So that incidence is about 2%. All right, so that moves us to the second category of measurement in EPI, which is effective exposures. The first is odds ratios. So if you've not taken epidemiology, there are different kinds of study designs in observational epi, and the first kind is the case study. And this is kind of where you're looking at understanding exposures, and you need to have a measurement to understand the occurrence of exposure in a group compared to those who don't without the disease. That is the odds ratio. So this compares the occurrence of exposure in a group with the disease to those without the disease. Okay, so interpreting the odds ratio is based on what that value is. So if the odds ratio is equal to 1, you can assume there's no difference between groups. So there's no association between disease and exposure. If it's over 1, the odds of exposure is greater in the group with the disease as compared to those without. So this is the risky group. And the odds ratio being under 1, the odds of exposure is less than those with the disease as compared to those without the disease. It's the protective effect. So the understanding the interpretation of the odds ratio is fine, but how do you actually calculate it? So you put together what you might recognize as a contingency table, but in reality, this is just a straight up disease versus exposure table. So if in your study, you have to assess among people who have the disease, you recognize, so for example, people who have developed microencephaly, or infants who have developed microencephaly and might have been exposed to Zika. You might want to put their disease status in the categories in the columns there, and then go back and check, were they exposed to Zika? Yes, no, and put the numbers into this table. To calculate the odds ratio, you take the product of A and D over the product of B and C. So it's just like a giant X on this table. And that's calculating the odds ratio. You can then interpret the value compared to the value of 1, as I've just mentioned. And that will allow you to assess whether or not, again, going back to the slide, the exposure that occurred, the occurrence of that exposure in the diseased group has an association or not. So without the disease. So it's really a great measure to calculate, and it's relatively easy to calculate if you have this data. So when you're doing a case control study and you're going back and asking for case history cases, what were you exposed to? This is how you would do that. What is relative risk? So this compares risk of disease in an exposed group to the risk of disease in an unexposed group. So again, you are assessing you're looking at groups that with known exposures, their exposure status, and you're looking at the development of disease. And this is typically measured in cohort studies. So you know people's exposure status, and you're looking at the development of disease. So similar to the odds ratio, if you have a relative risk of 1, there is assumed to be no difference between groups in the exposure. And has no impact on the risk of disease. But if it's over 1, the exposure is associated with a higher risk of disease. That's the risky group. And again, under 1, the exposure is associated with lower risk of disease. So to calculate this, you need to calculate it's a similar calculation, but you need to understand the incidence of the exposed, the incidence of the unexposed. Again, you're looking at the occurrence of disease. So you have to understand the incidence of both groups, as you know whether they've been exposed or not. And in a cohort study, you follow people to see if they develop disease. So relative risk, again, you're looking at the group that has both exposure and then develops disease. You divide by that group and the product of A and D. And then again, you look at the group that has the group C, which has disease but was not exposed, and then you divide by C plus D. That calculation, again, go back to this interpretation table and it will tell you whether there is no evidence, is it risky or protective. Okay, so there's some basics of a very fast introduction to the types of measurements and calculations you can do in epidemiology. But the most important is to understand proportions, rates, and ratios. As we go through this course, you'll learn a little bit more about how to do this in Google Sheets. But I hope this gives you a good sense of how to start interpreting some of this information and to use these terms correctly.